Okay, so this is the video lecture for Chapter 3, Objective 1, Critical Numbers and Extrema. And I will give you a quick minute to record or to write down the definition of a critical number. Okay, so what is a critical number? So we have to have our function be defined at C. So C has to be in the domain of my function, and this will come up, so make sure that we are paying attention to that. So if our derivative at C is equal to 0, or if f is not differentiable at C, then C is a critical number of f. So what we are looking for are two things to occur basically. Is if our derivative is equal to 0, so this is saying the slope at that point is 0, so we have a horizontal tangent. So if I have a graph that does this, then this would be a horizontal tangent. And so then that value, x equals c, would be a critical number. That would be a critical number because the tangent line is horizontal. So what if the function is not differentiable? What does that look like? So that could be a couple of things that could happen if we have what we call a sharp turn. So if we have a sharp turn, our function is not differentiable there. So there's two schools of thought here on why it's not differentiable, maybe more than two. One, we know that a derivative is defined as a limit. So if I were to take the limit coming from the left versus the limit coming from the right, there's not a smooth transition, right? So the limit here is, or the slope on the left side is clearly negative, the slope on the right is clearly positive, and there is not a smooth transition to give us, what that sharp point can be, right? So the limits from approaching from the left and from the right would clearly not agree. Whereas on this one, the limit from the left is flattening out, going to 0. A smooth transition, right? The slope is changing. It's becoming steep, less steep until it hits 0. Versus here it's not, right? We don't have that, so then this would be not differentiable. But even though it's not differentiable, it's still considered a critical number. Okay, why? Because that's the definition, right? The slope is 0, or if the function is not differentiable. Okay, you could also have a situation where you have a vertical tangent, right? You could have a vertical tangent. And then that would be a point where you would have something that you took your derivative, try to evaluate it, and it would not give you a numerical value. All right. So find the critical numbers given the graph for f of x. So let's go ahead and do that. So we're going to do two different graphs. So for the first one, I'm just going to draw kind of a negative parabola. And then at the negative parabola, I'm just going to have this kind of shoot off to the left a little. And so this would be f of x. And then I'm going to have that turn at 2. And then the intersection here at negative 2. And we'll count up to positive 2 there. So we're looking for the critical numbers given the graph for f of x. So the critical numbers would be where the slope would be 0 or where the slope would not be defined, right? So where is it 0 and where is it not differentiable? So we call this a hill. So at the top of this hill, this would be where the graph levels out, right? So it goes from increasing to decreasing. So last year in Math 3, that was called a relative maximum, right? So increasing to decreasing, so we have a relative maximum here. So that's where the slope is equal to 0, so then there would be a critical number here, right? So the slope of that tangent, so I'm going to draw my tangent line there. So the slope of that tangent line would equal 0, and then that is occurring at x equals 0. And then here, this is not differentiable because I have that sharp turn, right? So that's sharp turn. So the slope of that tangent is undefined, and that's because of that sharp turn. And then that is occurring at x equals 2. So we have our critical numbers. Are at x equals 0 and 2. Okay. All right, let's do another one. Okay, so I'm going to just draw a cubic graph. So we're going to do section off to here and off to there. Okay, so I want you guys to try this one for me. So what do you think the critical numbers are? Okay, talk to your neighbor, figure that out. Do you guys agree where your critical numbers are? And so we would say our critical numbers are at -1 and +1, or plus and minus 1, right? Either way. So at -1, +1. And so why is it at -1 and +1? Because I have a horizontal tangent line there and a horizontal tangent there. So if I were to take the derivative of this cubic and evaluated it at -1, I would get 0. And if I were to take this cubic derivative and evaluate it at +1, I would get a slope of 0 as well. So the slope of the tangent line is 0 here and here, and that would be it. Okay. All right, and let's do one more here. Okay, so go ahead and draw the picture. So we have a parabola here, and then the x-intercepts are at -1 and 1, and then at -1, -2. So the directions are still the same. So at the top, the directions are still the same. Find the critical numbers, okay? Find the critical numbers, okay? But now for this one, I want you to find them still for f of x. So what are the critical numbers for f of x? So f of x has critical numbers at x equals what? But pay attention to the fact that we have an f prime graph. So I'm not looking at f of x, I am looking at f prime. So this is my derivative graph. I still want the critical numbers for f of x. Okay, so remember what the definition is, where f prime is equal to 0 or undefined. So this is a parabola, so it's not undefined anywhere. So where f prime is equal to 0, that is where f has critical numbers. So this is f prime. So where would it be equal to 0? Is it equal to 0 here? No. Right? Equal to 0, that does not mean that. That means x-intercepts, right? So where are my x-intercepts? My x-intercepts are here and here. So I have a critical number for f of x, right? Not for f prime, but I have a critical number for f of x at -1 and 1. So f prime is equal to 0 at 1 and -1. So where would f of x, so the graph I can't see, right? The graph I can't see has critical numbers at -1 and 1. So if I were to redraw this graph, what would this graph look like, right? Well, I do know, but we're not going to talk about that today. Okay, so, but what I know is by definition, so I can't see the original, I can only see its derivative graph. So the original graph, whatever it does look like, it would have a max, relative max or min at -1 and 1, right? Which is not this picture, obviously, because this is the derivative graph. Okay, so that's a little bit tricky. That's like, you know, we just need to think about kind of thing. Okay? All right. Let's go ahead and move on to the next one. Let's zoom in and focus. Okay, so go ahead and write this question down and we'll go over it in just a second. Okay, so let's go ahead and write down our steps here. So we want to find the critical numbers for a function, so instead of a picture. So the first thing we want to do is we want to find the derivative. So that's our first step. We want to find f prime of x. So that's our first step. So in order to take this derivative, remember x cubed over 3, that's the same thing as 1/3, right? So I'm going to put a 1 here. So this is really 1/3 x cubed. So when I bring this, so I'm just doing power rule, so I'm taking the derivative here. So I'll bring down the 3, but 3 divided by 3 will be 1, so that will end up canceling. So I'll just have x squared, and then the derivative of x is 1. So this would be 3x squared over 3, but the 3's cancel. Okay, so now step 2, once I find the derivative, I want to set f prime of x equal to 0. Okay, set f prime of x equal to 0, because I want to know where the derivative would be equal to 0. What number do I need to put in for x to get a 0? But I also want to look for where could it be undefined. And that would be, you know, when would the denominator equal 0, right? When it's undefined is when your denominator is equal to 0. So I don't have a place where I have a denominator, so it won't be equal to 0. So I'm going to go ahead and just set it equal to 0. So replace f prime with 0. And so I can factor it, add 1 over, lots of different ways to solve this. Okay. So I'm going to just factor it. And so x will equal 0 when this factor is 0 or that factor equal to 0. So that would be at -1 or +1. Okay. And so then that is my critical number. So then f has critical numbers. I don't need to write this line down. This is just for the sake of notes. Okay, so f of x has critical numbers at x equals 1 and at x equals negative 1. So let me throw my negative in there. Okay? So how do we find critical numbers given a function? You just take your derivative and then set it equal to 0. And if you had a place where it might be undefined, would be where your denominator could potentially equal 0. But do remember that your critical numbers do need to be in the domain of your function. So be careful with the undefined components. Okay? All right, so let's take a look at definition of extrema. So for this part, I just want you to write down that bottom, right? So don't worry about this paragraph. I want you to just write that part down. So I'll give you guys a second to do that for me. Okay, so definition of extrema or extrema. So absolute extrema. So let your function be defined on an interval I containing c. So you have so f of c is a y value. So your y value is the minimum of your function on that particular interval if it is less than or equal to your function for all values of x and I. So what is it saying? It's the lowest y value on the interval. So if it's the smallest y value, if there is the smallest y value on your interval, then that is called your minimum. So your maximum, f of c, again, is your y value. So that is a maximum of your function on I if f of c, so your y value, is greater than or equal to f of x for all values of x on I. Okay, so basically your highest and your lowest y value on whatever interval you are, that is our max and min. Okay, so that is our max and our min. Okay, so do not write this down. This is just for us to talk about. So this is just for us to talk about. So I'm just going to read it and we'll talk about it here. So the minimum and maximum of a function on an interval are your extreme values or extrema of the function. Okay. They are also called your absolute minimum and absolute maximum on the interval. Okay, so your minimum is also called absolute minimum, max is also called absolute maximum. So at some points this can get a little confusing because we'll talk about relative extrema, because you know that from last year. Relative extrema, when you go from increasing to decreasing, we call that your relative maximum, which is not usually your absolute max. It can be, but it doesn't have to be. Okay, so, and a function doesn't have to have a minimum or a maximum on an interval, right? If you look at just any kind of line, right, it goes up forever, down forever, so it doesn't have a max, doesn't have a min. Continuity can also affect that, right? So continuity or lack of it can affect the existence of both a min and a max. Okay, so again, you don't need to write that part down, okay? All right, so go ahead and write down the extreme value theorem, and then we'll talk about that. So again, you don't need to be writing that down, just write down your extreme value theorem, and we'll talk about that in just a second. Okay, extreme value theorem. So if f is continuous on a closed interval, then f has both a minimum and a maximum on the interval, okay? Has both a minimum and a maximum on the interval. Okay, so it has to be continuous, right? And it has to be a closed interval for this to be true, okay? So just situations in general where are kind of just what we're thinking about. So if we just go from A to B here, so just like a little picture just to give you an idea. So if I put a dot here and I put a dot here, okay? So to go from straight across, right? If I went straight across, then it would have both a min and max, and they would be the same value, right? Because it would have its highest value would say be at 3, but so would its lowest value. So we would say, which is kind of silly, but that could happen, right? We would say it has a minimum at 3, a max on 3 as well. So why is that? Again, going off of our definition, because of the equality, right? It has that equality component on our definition. And so that's kind of the weirdo thing. But otherwise, when you go from here to here, right, you can go, you know, something like that. And so you would say its minimum is at 3, right? The minimum would be at 3, and its max would be however high that graph happened to go, okay? And then if you flip it around, it would be kind of the same idea. Okay, so the weirdo thing, though, is if it's constant, right? So, which isn't very helpful, but whatever, right? It is what it is. Okay, so let's go ahead and take a look at an example here. So go ahead and write this one down for me. Okay, so what are our steps here? Okay, so our steps. Okay, so step 1, we want to find our critical number. So we know how to do that already, right? So we're going to set f prime equal to 0 and also look for where it would be undefined, right? So where is our derivative equal to 0? Where is it undefined? Okay. So x squared's derivative is 2x, and the derivative of 2x is just 2, and the derivative of a constant is 0. So take your derivative, so 2x plus 2, and then we're going to set that equal to 0, no place where it's undefined, and then just solve for x. So I'm going to subtract 2 and divide by 2. And then now I'm going to evaluate the endpoints and critical number into f of x. So I have my critical number here, and then I have my endpoints here. So I have to look at my endpoints, and I have to look at my critical number. So what am I doing? So step 2, I need to take the x value, -2 and 3 and -1, and substitute it into f of x. So why am I doing that? I'm looking for the highest y value and the lowest y value, right? Because our absolute extrema, highest value and lowest value on my interval. So I'm going to evaluate -2 into my function. So I'm going to replace all my x's with -2. So -2 squared plus 2 times -2 minus 4. So 4 minus 4 is 0, and then minus 4 is -4, so -4. And then now I'm going to do the same thing and evaluate 3. So 9 plus 6 is 15, and then minus 4 is 11. And then finally, my critical number. So 1 minus 2 is -1, and then minus 4 is -5. And so finally, we just analyze, right? So we analyze our results. So the highest y value is our max, and the lowest y value is our minimum. So I have -4, +11, and -5. So my maximum would be 11, right, which is occurring at x equals 3. And then my minimum is my lowest, which would be -5, which is occurring at my critical number. So my extrema are 11 and -5. Okay? So when I'm looking for my absolute extrema, make sure you're paying attention that the only place we're looking are at our critical numbers and our endpoints, right? So we're only looking at our critical number and our endpoints, and that's where we always look for our extrema, okay? All right, last example. Give you guys a second to write this down. Okay, so we're going to start our first interval from -2 to +2. Okay, so I'm going to go ahead and graph this so we can get the picture here. So we're going to do it from a visual. So this is just a semicircle with radius 2, right? That's from our parent graphs that we worked with last year. So this would be just a semicircle with a radius of 2. And it's closed at the -2 and the +2, and that's what the brackets are, right? So brackets give us closed intervals. So we just want to look at the picture and figure out what's our max and min. So we're just looking for where is the highest the function goes, where is the lowest it goes. And we don't want to know like where it's located, just what the value is. So if I look at this picture here on my semicircle, where is the highest? So the highest is up here, right? So the highest it goes, which is on the y, it goes up to 2. So my highest, right, which is my max, so my max value would be 2, right? I don't need to know that it occurred at 0, I just need to know that it went up to 2. So my min, where is the lowest? Where is the lowest? So the lowest is here and also here, right? So they're at the same y value, they're just at different x's. So where's the lowest? It's at 0, it doesn't go below 0. Where does it occur at 2 different places, but we don't care, right? We just care that its lowest value is 0, so its minimum would be 0. And one more here. Okay, so it's still the semicircle. With a radius of 2. And then for our interval, we are closed on the -2 and open on the 0. Okay, so maximum. So I'm only looking from -2 to 0, right? So I'm only looking on this section here now. So I'm only looking here. So the maximum we know would occur right here, right? Except that it's an open dot. So it's not equal to 2. It approaches 2, but it's not equal to 2. So because it's an open circle, we would say there is no max, right? It would normally be 2, but it's an open circle there at x equals 0, y equals 2. So then that is where it normally would be. It's not allowed to be that because it's an open interval, so it would be none. And then we can't say, well, what about 1.9? Because then I would come back and say, well, what about 1.99? And then you go, what about 1.999? And then you could say, well, what about 1.9 repeating? Except for, hopefully you learned last year, 1.9 repeating is not about equal to 2, but is equal to 2, right? So we can't even do that because, again, 2 is not on the interval. So there is no maximum that occurs because it would have occurred there. So the minimum, though, the minimum one is easy, right? Minimum is, where is its lowest value? Closed dot, still there, so our minimum is 0. All right, and so hopefully that's enough to get you through the homework for tonight, and we will just chat and check back in with you guys at the next class.